Well, I will try to talk a little bit about the relationships between chemistry and physics. This is my subject matter. And so the outline of the talk is first a little short introduction about the problem of molecular structure. Then I will state the problem with a little bit precise formulation. Then I will see different ways of conceiving molecular structure, because we are talking about molecular structure, what it is. We have to understand each other about what we are talking about. And then finally, I will go in the main part of the talk about the three problems that are associated to the problem of molecular structure. And the question will be if solving these problems, solve the problem of molecular structure. Finally, the conclusions. So, the introduction. In philosophy of chemistry, perhaps the hottest topic is the relationship between chemistry and physics. You know, reduction, emergence, independence. Well, this is a very, very strong discussion. And in this context, the problem of molecular structure plays a central role. This problem can be expressed by a question, as any problem. The question is, can molecular structure be explained exclusively in quantum terms? This is the question we will face in this talk. I want to say some things about the problem, which the problem is. In this case, I think that it is necessary to distinguish between the problem of reduction and the problem of elimination. One thing is reduction, whether the concept of molecular structure can be explained exclusively by means of what quantum mechanics offers us, laws, concepts. Then we can discuss if the model of reduction is Nagelian or Nagel-Schaffner or whatever, but this is the problem of reduction. That is completely different to the problem of elimination. That is, whether scientists can someday, I don't know when, can dispense with the concept of molecular structure when they are pursuing their explanatory and predictive goals. Why? Because perhaps the goals in the future are different. I don't know. Perhaps the very concept of molecular structure is not useful anymore because they are looking for different things. So it is important. It is relevant to take care of the distinction of these two problems, because they are different. For instance, Aristotelian cosmology or phlogiston theory were not reduced, were eliminated, were left aside. Nobody tried to reduce those theories. So I'm not interested in the future of quantum chemistry or chemistry or quantum mechanics about how we will describe substances at the microscopic level. I want to focus in the problem, in the concept of molecular structure like it is used today. So the problem is the problem of reduction, not the problem of elimination. I think that this is important to distinguish. The third point to take into account is what is molecular structure, because it's a concept that receives different senses, at least three, perhaps more. I found three very different. The first one is molecular chemistry. Molecular structure, it refers to the spatial arrangement of the atoms in the molecule and the chemical bonds that hold them together. Okay, this is molecular chemistry. What happened in quantum chemistry? A first characterization of a molecule is a system in physical space composed by nuclei surrounded by inert inner shell electrons placed in the definite positions and bonds explained in terms of interacting electrons, those bonding electrons. And the structure of this system is defined by this element in their spatial arrangement. This is what Brian Sutcliffe said me when I said, for you, what is molecular structure for you? This. But there is another more quantum concept of molecular structure that comes, yes, closer to quantum mechanics. You can find this in Hans Primus. A molecule, from this view, is a system in which the nuclei are placed in definite position. They constitute a potential in which the electrons, which are quantum, the electrons are quantum particles, electrons move on that potential. The structure of this system is defined by these elements in their spatial arrangement. So, in any case, the concept involves a strong spatial connotation regarding at least the position of the nuclei. Then we can discuss about electrons, but at least the nuclei have a definite spatial, the concept has a spatial connotation about the nuclei. So, after this introduction, let us go to these particular problems. First, the Born-Oppenheimer approximation. Let us consider the Coulombic Hamiltonian. The quantum Hamiltonian. For the quantum mechanics, this is the Hamiltonian. You have kinetic energy of nuclei, interaction of nuclei, kinetic energy of the electrons, interaction between electrons, interaction between electrons and nuclei. Okay, you have everything there. The first step of the approximation is to clamp the nuclei in definite positions. So these R's, big R's, which were operators, become parameters, not operators anymore. With this Hamiltonian for the electrons, I can solve the Schrödinger equation, obtain the different energies, in particular the ground state energy. If I repeat this procedure many times with the positions of this parameter, changing the value of the parameters, then I can obtain the energy for all these positions. So I can obtain the potential. I make like this because it's like a hypersurface, so hypersurface, where the electrons move. So then I obtain the Hamiltonian of the nuclei, adding the kinetic energy of the nuclei, and then I obtain a full Hamiltonian, adding the original electronic Hamiltonian. This Hamiltonian, and this is the independent, if you can follow all the steps. This effective Hamiltonian is not Coulombic. It's a Hamiltonian has not the original symmetries because it was obtained through all this procedure. So, from the viewpoint of quantum mechanics, we have two things to say about this procedure. First, when you place the nuclei at definite position, we are violating the Heisenberg principle. This is a kind of counterfactual approximation, but counterfactual approximations that are used in science not always are legitimate. They are valid when they can be replaced by a factual one. And this is a case, this is something that cannot be done when you are violating a principle of the theory. I mean, I want to be clear. I'm not saying that molecular structure is a metaphor or is something that is not useful. I'm very realist about molecular structure, but I'm not realist about molecular structure in the field of quantum mechanics. This is something that Hasuk Chang says, and we can discuss then in the questions the difference between legitimate and not legitimate counterfactual approximations. And there is another point, is that from the viewpoint of quantum mechanics, if you change this Hamiltonian, you change the system, because the identity of a system is it's Hamiltonian. So when I change the Hamiltonian, the quantum Hamiltonian by an effective Hamiltonian, I'm changing the quantum system. So this is not an approximation. In Norton's terms, in this paper about approximation and idealization, we can come back to this point also in the questions. This is not, strictly speaking, an approximation. It is an idealization, and idealizations are different because when you change the system, you can use it. Of course, it's legitimate to do that, but to draw ontological conclusions from an idealization is something very difficult. I mean, it has to take with much care. So I know that there are recent works that go beyond the Born-Oppenheimer approximations, where nuclear electrons are treated on equal footing. I have not studied this kind of works in detail yet, but I could read them, and I see that the first step is to say, well, I have the ground state, and I will treat electron as nuclei in this on equal footing. So this is the form of my ground state. But here we have to take care, because from the viewpoint of quantum mechanics, we are assuming separability. And we know that in quantum mechanics, when you have systems that have interacted, in general, you have entanglement, and entanglement implies non-separability. You cannot explain a state as a product of the states of the components. So there is something here interesting to be, investigated or thought. Is this an approximation? Is this an idealization? Okay. So let us pass to the two following problems, because they do not depend on the Born-Oppenheimer approximation. In a certain sense, they live beyond the Born-Oppenheimer approximation, because they start from the complete Hamiltonian. The complete Hamiltonian, this is the same I wrote before, so the terms are exactly the same. They have a complete Hamiltonian of any quantum system, and a molecule in particular, has many symmetries. The Galilean symmetries, due to the group of the symmetry of quantum mechanics; permutational, due to particles of the same type; Coulombic, due to the kind of interactions. What we know is that when the Hamiltonian has those symmetries, the eigenstates of the Hamiltonian has exactly the same symmetries. This is a mathematical fact. So in particular, the ground state, that is one of the eigenstates of the Hamiltonian, must has the same symmetry as the Hamiltonian, as the complete Hamiltonian, the quantum Hamiltonian. We are talking about quantum mechanics now. So the problem is that molecules display certain asymmetries that are not embodied in the ground state. How can we explain them? Let us take the case of chirality. Chirality is the property of a molecule to rotate polarized light in one direction and in another direction, and it's thought that the disposition is of the elements of the molecules is one is the mirror image of the other. So chirality, according to quantum mechanics, the system is in a left rotation or right rotation states, and this is the two states we see when we measure, and they are eigenstates of an observable, let us call it chirality. the Hamiltonian, which is Coulombic, depends only on the distances of the particles. So it's not handed, has no chirality. It has a parity symmetry, and if the Coulombic Hamiltonian has this symmetry, its eigenstates, in particular, the ground state, has the same symmetries. So the ground state, if I want to recover the symmetry of the ground state, I have to make a superposition of the two asymmetries with the same weight. This is the expression of the ground state in terms of the superposition of left and right states. The same conceptually, the same happens with other asymmetries of molecules. For instance, in the electric dipole moment is a value that changes, might change in different direction of space, and all these states are eigenstate of observable, let us call, electric dipole moment. But the Hamiltonian is non-directional. It's non-directional. It has rotational symmetry. This is due to the Coulombic nature of the interaction. So the ground state also has to have this symmetry. How can express so the ground state in terms of this asymmetric state? I have to make in this case, an infinite superposition, infinite in all the direction. This is an infinite sum, is an integral, an infinite sum of all the possible directions. So what this case shows is that a symmetry is reconstructed by superposing all the possible asymmetries with equal weights. This is the way in which a symmetry is reconstructed. All the asymmetries, I spell very badly, asymmetries with the equal weight. It must be an equal weight, because if the weights are different, this asymmetry reappears. Let us take the case of chirality. That is easier because you have only two cases. I have this ground state, but when I measure, I see one of the components. And what happened? Well, this sounds analogous to the quantum measurement problem. In fact, we have a work in which we show that if you have an acceptable account of the quantum measurement problem, you can answer the symmetry problem. In this paper, we applied our interpretation of quantum mechanics. We can come back to this in the questions, because in this interpretation, measurement is a process of symmetry breaking. So this is not, in this case, it's not surprising, but you can use another interpretation. If you obtain, if you have an argument that obtains this from this, so you've answered the symmetry problem. The question is the solution of the symmetry problem a solution of the problem of molecular structure? This is the question. When I obtain L, for instance, I've solved the problem of measurement. What I can show is that the observable C has value L. No? L means that it rotates to the right. But this still says nothing about the many other observables of the system, in particular, the positions of the nuclei and the electrons. In other words, or in quantum words, this observable chirality with its two eigenvalues, it's a strongly degenerate observable in the Hilbert space of complete Hilbert space of the molecule. What means that there are many spatial configurations of the component of the molecules compatible with C having the value L. There are many ways of being left rotating or right rotating. Being left rotating does not fix the positions of the components of the molecule. Well, let us go to the problem of isomerism that it's more serious. You know that isomers are molecules with identical molecular formulas, that is the same number of atoms of each element, but different arrangement of those atoms in space. This is what are isomers in chemistry. And it's interesting that in chemistry, each isomer is described by its effective Hamiltonian, obtained, as we said before, the Born-Oppenheimer approximation. This means that in chemistry, isomers are treated as different systems, not as the same system in different states. Isomers are different kinds of systems. And this is pretty reasonable because from the viewpoint of chemistry, isomers are very different because they can have very, very different chemical properties. So thinking in them as different systems is completely reasonable. The question is, what can we do with this from quantum mechanics? Let us again take the complete Hamiltonian. The complete Hamiltonian, it's interesting, but because the Hamiltonian is the same for all isomers, because I don't know if you see the arrow, these that have little hats are operators. So they do not depend on precise position because there are not precise positions. These are not scalars, these are operators. So in a certain sense, we can say that the Hamiltonian is blind to the particle's position. Or we can also say that the Hamiltonian is symmetric respect to the different spatial configurations. In a certain sense, it seems to be a particular case of the problem of symmetry. It's something that Vanessa says and Franklin say in their paper. Perhaps the problem of symmetry is more general, and the problem of isomers is a particular case. But this case has a peculiarity. The question is, can we appeal in this case to the same strategy as in the case of the symmetry problem, the same strategy as in the case of chirality, for instance? Well, let us try. If we apply the same strategy, we obtain the ground state, and we say that the ground state is a superposition of many asymmetric states. This is the symmetric ground state, and these are all the asymmetric states corresponding to isomers. Okay, we can think about this. If we think in this situation, when we obtain one of the isomers, we can think that this is analogous to the case of quantum measurement as previously. But now let us recall the mantra we said before. A symmetry is reconstructed by superposing all the possible asymmetries with equal weights. So it means that I should include in this sum all the possible spatial disposition of the components of the molecule. If we want to forget electrons, forget electron. All these possible dispositions of nuclei. The problem is, this is what I say, the sum should include all the mathematical possible configurations, and all the C sub I should be the same. But here the problem is that when I have the number of the type of element that compose a molecule, in general, we have only few nuclear configurations that we obtain experimentally. That is, only few isomers are considered effectively real, not potentially infinite. 2, 3, 5, not more than this. Of course, in quantum chemistry, this is explained in a quasi-classical way. Put the nuclei in precise positions and write or draw the energy hypersurface, and then see the minimums, and these are the possible. But this is a quasi-classical reasoning. This is not quantum. This is the point. I have to relate to Born-Oppenheimer approximation. 2 final and further remarks. First, when I have this asymmetric eigenstate, that is the eigenstate of the effective Hamiltonian, because if not, it could not be asymmetric. This, viewed from the viewpoint of the quantum Hamiltonian, is not an eigenstate of this quantum Hamiltonian. This means that this state, if I had let us suppose that I find in some instance the molecule in this state. This state would immediately evolve to different states. I cannot think in this state as a ground state, a stable ground state of a molecule. This is something that Claverie and Diener says very clear. How can we explain that in the course of time these initially localized, for instance, this one, states retain their localized character? Even if we are prepared to concede that the localized state different from the molecular eigenstates, the T0, has been created by the interaction, the molecular Hamiltonian alone, this one, is unable to maintain this localized character in the course of time. This is another problem. And the second remark is that let us consider the symmetric ground state that is symmetric, of course, and it lives in the Hilbert space of the complete Hilbert space of the molecule. This Hilbert space can be expressed as a tensor product of the Hilbert space of all the electrons or nuclei or the, okay. This is what we think when we are thinking in little systems, little particles, yeah? But in quantum mechanics, you can make different decomposition, different tensor product structures. This is the name. So it can be shown that given a Hilbert space, it can be decomposed in different ways. For instance, in another way, where nuclei and electron can no longer be identified, which are the entities that are related with each one of these. I mean, if a system is represented by a Hilbert space, well, these are not electrons or nuclei. These are different entities. And this is the problem in quantum mechanics, that it's very difficult to think about this kind of entities. If you want, we can come back in the questions on this point, because there are very simple examples we have even published, but they are example used for people working in TPS, in quantum mechanics, where you see how, for instance, you take the hydrogen atoms, and if you decompose the Hilbert space in two different ways, you obtain things completely different. you obtain completely different subsystems. Well, and there is no criterion from quantum mechanics to privilege one TPS regarding another. Conclusions are very simple. Well, I think that there are strong obstacles to explaining molecules exclusively in quantum terms. Someday will scientists dispense with the concept of molecular structure and they will use only quantum mechanics? I don't know. It's possible. It's difficult to believe for me, but it's possible. But I mean, this is not the problem. The problem is the problem of reduction, the problem of explanation of this concept of molecular structure, the concept of molecular structure that now quantum chemists are using. And even if someday molecular structure is left aside, like Phlogiston, this will not offer a positive answer to the problem of molecular structure as I formulated it at the beginning. So I think that I'm pretty close. Thank you.